Good afternoon, everyone. Welcome to today's talk given by Arjun Kar from UBC. He will tell us about a hierarchy of complexity growth from integrability and chaos. Please take it away, Arjun.
All right. Thank you very much, Dongshin. Thanks for the invitation. I'm very happy to be virtually back in Warsaw. And yeah, as Dongshin said, I'm going to tell you about a couple of recent papers, one from about 2 years ago, and then one much more recently. It's all joint work with Vijay Balasubramanian, Matt DeCross and Kathy Lee, who are two graduate students at Penn, and Onkar Parikar, who's currently a postdoc at Stanford, soon to be moving to TIFR. All right, so let me just remind you, I think probably this audience needs no reminding, but in case you do, complexity theory is a subject which asks how many simple objects are necessary to create a complicated object. And in quantum mechanics, the building blocks are usually simple local unitary operators. So here I've drawn for you a very simple quantum circuit. Each one of these lines you should think of as a small Hilbert space, perhaps a qubit. And each one of these gray boxes is a simple local unitary operator drawn from some perhaps finite set of operators that acts only on 2 qubits at a single time. And the general idea is on this right-hand side, we have some state perhaps, or maybe a unitary operator. And we're trying to ask how many of these small gray boxes, these small local unitaries, are necessary to create some output state or unitary operator. And in quantum gravity, the complexity of unitary operators and quantum states was identified as a potential probe of the black hole interior by Susskind. So let me just remind you how that goes. The basic intuition in the ADS-CFT correspondence, really the only model of non-perturbative gravity that we understand, comes from the thermal field double state. And that has an entropy, a bipartition entropy across left and right copies that scales like the number of degrees of freedom. So these states, ket n, are just the CFT energy eigenstates. And the large n parameter, I'll denote capital N throughout this talk, just to represent the number of degrees of freedom in any system that we're considering, whether that's quantum mechanics or quantum field theory, so on. And correlation functions of some generic operators in this state reach their late time values relatively quickly by times that are upper bounded by polynomials in the number of degrees of freedom. So I'll write a general polynomial as capital N is the power alpha, where alpha is some fixed number. So 2 examples of such correlation functions are the time ordered and out of time ordered 4-point functions studied in great detail, especially the out of time order one in this paper. So I've written here for you those objects and their asymptotic forms in Lorentzian time. And you'll notice that the time ordered correlator, this top line, reaches its late time value, which is just the factorized product of thermal 2-point functions, at a characteristic time, which is order beta. So that's actually order 1 as a power of n. And the out of time order correlator has a slightly different time scale. It reaches its late time value at a time of order log n, which is sometimes called the scrambling time. But both of these times, you'll notice, are certainly upper bounded by polynomials in the large n parameter. In fact, both of these are upper bounded by a linear function of n. But longer time scales are achievable. But we can look at the dual geometry to the thermal field double. So I've drawn for you here the gravitational dual, which is the 2-sided eternal black hole. And it's easy to construct quantities in this bulk dual, which at least appear naively to have non-trivial growth for much longer than polynomial times. Or if general relativity is a good description of this region of the interior for a long time, then they would have non-trivial growth for much longer than polynomial times. And one such quantity is the volume of a maximal space-like slice. So the procedure is you pick 2 times on the left and on the right, T1 and T2, and you draw a space-like slice through the bulk, and you try to maximize its interior volume. And the slice which does the job is this blue one. So of course, this red slice is a perfectly good Cauchy slice associated with these 2 boundary times, but it does not maximize the space-like volume. So the one which maximizes the volume is this blue slice. And as we move these times into the future, the volume contained in the interior of this slice will increase. And at least classically, that volume increases without bound. So it increases indefinitely into the future as we increase these times. So Susskind conjectured, and later arguments were provided by Stanford and Susskind, that the quantum complexity of the thermal field double state to this bulk volume, the volume of a bulk space-like slice. And some evidence was given by ADS shockwave calculations in this paper. But more generally, stepping back from the thermofield double for a second, Susskind conjectured a more general pattern of complexity growth for the time evolution operator. So this is the operator complexity rather than a state complexity. I'll draw that as curly C of this time evolution operator. And this conjecture is supposed to hold in maximally quantum chaotic systems. So let me just describe what it should look like if I have a system of, say, n qubits, and I want to understand the complexity of this time evolution operator. The expectation of Susskind is that this complexity should grow linearly with time for a time which is exponential in the number of qubits n. It should then saturate at some value, C max, which is exponential in n. And at this saturation, there will be a complexity plateau. There will be some small oscillations around the plateau. And eventually we'll hit the Poincare recurrence time, which is doubly exponential in n, and have some kind of recurrence where the complexity drops down. And there's a sizable dip instead of these smaller fluctuations around the plateau. So this plot represents the expectations that Susskind gave us. And I want to just highlight two features of this plot that will concern us today. So the first is this early time growth rate, the slope of this early time region before saturation. And one expectation is that that growth rate should obey in appropriate units. This time derivative is equal to 1. So this growth rate needs to be constant. That's an expectation of maximally chaotic systems until a time which is order exponential in n. And furthermore, the plateau height should be exponential in n itself. So those are two expectations for maximally chaotic quantum systems that I want you to keep in mind. But today we'll be dealing with not just maximally chaotic systems, but also free and integrable systems. And we'll compare and contrast these quantities. So before I get into the actual talk, I want to just give you the results. So here's what we found. On the growth rate side, we provide two theorems that relate familiar properties of physical systems to these growth rates before saturation for any Q local Hamiltonian H acting on some Hilbert space which has dimension e to the n. So the first theorem, which you might call the creation annihilation theorem, says that if there exists a K local creation annihilation operator, curly O, whereby creation annihilation, what I mean is that the commutator of this operator with the Hamiltonian just gives back the operator itself along with some constant. With K less than or equal to Q, so the locality of this operator is at most the locality of the Hamiltonian, then we have that the time derivative of complexity is less than 1 at some time after a time t star, where t star is defined by 2 pi over this eigenvalue lambda. And for K greater than Q, so if this operator is more non-local than the Hamiltonian, a similar result holds, but the time scale is shifted. So instead of 2 pi over lambda, time scale that we have a slowdown in complexity growth is now 2 pi over lambda times e to the n. The second theorem involves a matrix M, which is a matrix of smeared infinite temperature K local operator 2-point functions, where again, K is less than or equal to Q, defined by this expression. So these TAs are a basis for all K local operators, where K is less than or equal to the locality of the Hamiltonian. And we simply take their Lorentzian evolved 2-point function, and we take the expectation, just a trace of this expression, which can be thought of as the infinite temperature thermal 2-point function, and then we smear in Lorentzian time. So we integrate over a box of size t in Lorentzian time, and that defines this matrix element MAB. Now we construct this matrix, and if we can find a time t star at which M has a 0 mode, then we can again conclude that there's a slowdown in complexity growth after a time t equals t star. So just as a potential application of these theorems, one thing that you could try to do is, if in a maximally chaotic quantum system, if you were able to find a K local creation annihilation operator or a 0 mode of this matrix M at a time which is only growing polynomially in n, you would be able to disprove Suskind's conjecture. So these two theorems allow you to prove that there are slowdowns in complexity growth. So of course, in maximally chaotic quantum systems, we don't expect such things.
So the setup. So the setup that you're considering is a setup of quantum many-body system, not the quantum field theory.
That's right. Yeah. So this talk will be entirely in finite dimensions. Yeah. Although there are situations in which these expressions, in particular, this expression commutation with the Hamiltonian and the definition of this matrix M as a thermal two-point function, these both make sense directly in quantum field theory, right? So we won't deal explicitly with any quantum field theories in this talk, but at least personally, I won't prove this for you, but I believe that quantities like this could be computed in quantum field theory very explicitly. We haven't done that though. We focused on finite dimensional systems. Any other questions about the growth rate theorems? All right, very good. So here are the results on the plateau height. So here we're going to give some results on the quantity C max that I defined on the plot before for you. And so as Mikhail asked, we focus mainly on theories which involve n Majorana fermions, or equivalently n over 2 qubits. But our results are valid for arbitrary Q local Hamiltonians, where Q does not scale with n. So the form of such Hamiltonians would be very familiar to you. They look like this with some couplings J. And here the size are our Majorana fermions. They have some anti-commutation relations. And by studying the complexity of time evolution for various choices of Q, the locality, and J, the coupling, we find the following hierarchy of plateau heights. So for free theories, which are defined by Q equals 2 models with arbitrary couplings, we find that there's a complexity plateau at an order square root of n value. And we're able to analyze this plateau value very precisely, as I'll show later. For integrable systems, where Q is greater than 2, so it's not a free theory, but the couplings have been restricted in order to ensure integrability, we find that the complexity is upper bounded by a polynomial in n. So the precise power is actually Q divided by 4. This bound is only an upper bound on the plateau height. We are not able to prove that the complexity actually becomes that large, but it's just an upper bound. So that's the reason for this less than or equal to. Now, finally, in chaotic systems, one example which you might be very familiar with is the Q equals 4 case, where these couplings J have been drawn at Gaussian random. That's sometimes called the SYK model. In the chaotic case, relying only on very general properties of the spectrum and eigenstates, we're able to show that the complexity reaches an order e to the n height modulo a concern that I'll mention later. So there's a technical issue that enters in the definition of this approximate psi. So I'll explain that in more detail when we get there. But I want to emphasize that these results are also ordered in how precise in how much control we have over the system. So we have the most control over the free theory. Our results are most precise there. They're slightly less precise in the integrable system. And in the chaotic system, there's an issue which we actually don't have control over, which I will explain when we get there. Any questions about the plateau heights?
Yes, I have a question, not about the plateau height, but about the duration of the plateau. Like in this model, are you able to also say something about the duration of the plateau, like from e to the n to e to the e to the n?
Yeah, that's a great question. So we actually don't have control over that regime. Yeah, the regime of the plateau itself is very, very difficult to study in the model that I'll present. Yeah, it requires quite a bit of control that we don't have. I've thought a little bit about how to control that regime. It seems difficult for reasons that I think will become clear, but yeah, I'd be happy to talk more about that at the end.
Okay, sounds good. Thanks.
Okay, very good. So moving right along, here's the outline of what I'll tell you. First, I'll review geodesic complexity theory very generally, where all these results are derived. And then I'll just explain briefly the bounds that I told you about on the growth rates and the bounds on the plateau heights. And I'll conclude with some outlook. All right, so unitary operator complexity in this talk, we will formulate it as a distance on a Lie manifold. And that Lie manifold will be this special unitary manifold acting on the dimension of the Hilbert space. So we will use that as a space of all operators that act on the Hilbert space. And the metric we will need is right invariant. It's a particular right invariant metric on this Lie group. So let me just remind you that a general right invariant metric is specified by a metric on the Lie algebra, which has generators that I'll label TI. We have the usual Lie bracket relationship where F is the structure constant tensor. And it's natural to pick a basis which has a notion of locality. Two familiar examples are the n-Majorana basis and the n-qubit basis. So for n-Majorana fermions, the Hilbert space has dimension 2 to the n over 2. And a basis of operators, Ti, that we might construct are products of those Majorana fermions. So for example, this entire Lie algebra is spanned by including the one fermion objects, which are just the individual fermions. We can also have products of the fermions like psi1, psi2, with appropriate factors of I to make sure that these objects are all Hermitian. So we take all possible products, and that gives us 2 to the n minus 1 operators, which form a basis for this space. Similarly, there's an n-qubit basis, which has Hilbert space 2 to the n for n qubits. And in that basis, we just take all possible tensor products of Pauli operators acting on each of the n qubits. And the notions of locality should be fairly clear from these bases. The notion of locality in the Majorana basis, for example, we would say that one fermion operators are one local, two fermion operators are two local, and so on. Now, the choice of a basis which has a notion of locality allows us to implement a restriction to simple operators. So remember, complexity involves some restriction. So you don't consider everything to be simple, but only certain operations are simple. And this arises as a choice of a subset of generators. So we're going to consider a subset of those Ti that I wrote down, which will be considered simple in the complexity sense. And we will use that to define our right invariant metric on the Lie manifold. So if we have a Q local Hamiltonian, a very natural choice is to consider all K local operators such that K is less than or equal to Q to be simple in the complexity sense. So then the appropriate Lie algebra metric, which was originally written down by Nielsen and friends, who formulated this geodesic complexity formalism, is the following. So the metric on the Lie algebra takes TA and TB, which A and B are now simple generators. So they live in our subset of simple generators, and the metric is diagonal in that subspace, in the simple subspace of generators. Now, in the non-local subspace, or the hard subspace of generators, which I'll denote with dots, so these A dot and B dot represent the hard subspace index, the metric is again diagonal, but the coefficient is not 1 anymore. So the metric is diagonal, but the coefficient can be quite large. So we'll write it as 1 plus mu, where mu is exponential in n. So intuitively, what this metric is doing is, if you have a path that lives on the Lie manifold, if you have a velocity that points in the simple direction, the path length will be quite short. But if you have a velocity that points in the hard direction, the path length will immediately become large very, very quickly because of this exponential weight in the metric. So what this does is make sure that geodesics on that manifold are heavily incentivized to lie only in the simple directions. That's the intuition of this metric. Now, time evolution complexity is then just the distance in this metric from the identity operator to the time evolution operator. So that's our definition of this quantity.
Sorry, can I have like another question?
Yep.
So mu exponentially in n, it's an input, right? Like that's your choice, right? But you can imagine like other choices, for example, exponential in k or something like this, right?
Yeah, absolutely. You could imagine that this mu actually depends on which non-local operator you're looking at. And I think what you're asking is, could you have a graded choice of mu? So the metric would still be diagonal, but the weight would scale with the degree of non-locality of this operator, for example.
So that's one question. And the other question is if mu just sets the plateau, and then that's why you take it exponentially in n.
Ah, good. So yeah, the answer to your first question is you could certainly try to do that. You could have a weight that scales differently for different non-local generators, depending on the degree of non-locality. This makes the analysis somewhat more complicated. It's more difficult to solve the geodesic equation in that case. So we just took the simplest case here. but you could certainly extend the formalism to incorporate that. Yeah, it would be very straightforward. The equations you would have to solve become more difficult, and personally, I haven't solved them myself, so I don't know exactly how it would go, but there's no theoretical obstruction to doing that. Yes. Your second question was the choice of mu being e to the n. So this choice of mu being e to the n was actually put forward by Nielsen and friends. So this is not something that we put in by hand to make the plateau, but it's something that you need to put into this metric in order for this metric to reproduce circuit complexity. So remember, the notion of complexity that I defined at the beginning involved some choice of simple unitary operators and building up a quantum circuit. And in order for this notion of geodesic length or distance on a Lie manifold to be polynomially equivalent to that notion of complexity, circuit complexity, mu needs to be exponential in that. Yeah.
Okay, very good. Thanks.
That's the motivation for it.
And like if you were to think about taking I mean, if you consider a lattice model and you think about taking continuum limit, do you have like an idea of what you still call a simple operator? Like, would you call like the primary operator simple as well as, or descendants like get complicated at some point? Or
yeah, that's a great question. So I haven't thought about this in great detail. I think my first thought would be exactly what you say. So primary operators would be considered simple, and you would act with the symmetry generators like the lowering operators that take you to descendants. There would be some cutoff, some fixed cutoff on the degree that you can act with the descendants. So you can't act with an arbitrary descendant to make the energy arbitrarily large. There would be some cutoff, and beyond that point, you would call the operators hard. It's difficult to implement that in practice, I think, because it breaks the symmetry pretty badly. So you're starting to treat the different modes of the stress tensor differently in a 2D CFT, for example. So I'm not quite sure how the calculation goes, but my intuition would be exactly as you say. Yeah.
So if you were to implement this analysis, say in the Ising model, right? Like you would capture epsilon, sigma, right? Like as simple things as well as the energy density, right?
Yeah.
And momentum density, I guess, and that would be almost it, right?
Yeah.
From the spectrum of the theory.
You would have the identity, you'd have the spin operator and the epsilon operator. Those objects have some conformal dimensions. You would consider some finite cutoff on the number of descendants you're allowed to take, and then the action of L minus n would be considered simple as long as n is not too large. So beyond a certain point, you would start to consider those operators complex.
Yeah,
and then you could, you could try to compute distances, but the manifold would be infinite dimensional. It gets a little bit complicated. Yeah. But yeah, that would be the basic structure. Yes. Other questions?
Sorry, Arjun, I just had one because I didn't understand your answer exactly to this Michal question. So. So let's say you don't fix mu to be e to the n, but you fix it to some value. Is the Plateau value of Plateau related to mu then or not?
Let's see. It will be, yeah. So what we will see is that, in our analysis, we don't actually have to take mu e to the n. So we're able to write down, the formulas that I showed you previously, even when mu is arbitrary. So we don't rely on mu large in order to derive our plateau heights. It's only for mu large that the plateau actually reaches those heights, though. So for example, if you took mu equals 0, then the plateau would be at order 1. Actually, it would not be order e to the n, but it would be order 1. So the value of the plateau will depend on this this quantity mu, and it comes out in our formulas. Yeah. Like you can see just the explicit dependence of, say, the quantity C max on this mu parameter. Yeah. So that is necessary for the plateau to have the correct height. That's right. Otherwise, distances on the manifold are too short.
Okay, thanks.
Yeah. All right, moving right along. So the geodesic, so we have a Lie manifold. Now we need a geodesic equation, and the geodesic equation on this manifold with the right invariant metric actually has a very simple form in the correct variables, sometimes called the Euler-Arnold equation. And so here it is. I've written it for you on the left here. This G is just a metric that I defined before. This F is the structure constant, and V is some control velocity, sometimes called the control Hamiltonian. So you solve this equation for the velocity V, and to find the path that is actually traced on the manifold, you just perform this path-ordered exponential of the quantity V. Now, at sufficiently early times, what we were able to show in this first paper from about 2 years ago was that at sufficiently early times, there is a unique minimal geodesic that connects the identity to the time evolution operator. And we call this the linear geodesic. So linear geodesic is very simple. The velocity is just the Hamiltonian times time. So you just point yourself in the direction of the Hamiltonian on the manifold, and you start moving in that direction. So it's just the trajectory that's traced by time evolution itself. It turns out to be a geodesic. So now we have a geodesic. We want to understand when can this geodesic stop being minimizing? Or in other words, when is there another geodesic which would have a shorter length? Because we're interested in the distance rather than the length along a particular geodesic. The distance is just the length along the minimal geodesic. So in the geometric model, understanding obstructions to complexity growth just reduces to understanding the study of obstructions to distance growth. And obstructions to distance growth along geodesics come in two distinct classes. So the first class are called conjugate points. And conjugate points along a geodesic are points at which the geodesic may be deformed in such a way that the length and the endpoints remain fixed to a certain order in the deformation parameter. This first definition should not be intuitive. I'll explain it much more on the next slide. But the second way that geodesics can become non-minimizing is pretty intuitive. Those are called geodesic loops. And these appear at points where there exist two distinct geodesic segments with the same length and endpoints. So it's relatively clear that if you're running along some geodesic and you encounter a point at which there is another geodesic that takes a different path and arrives there, if you're continuing to run along the original geodesic, after you encounter this geodesic loop point, that geodesic will no longer be minimizing. There will be another geodesic which is shorter, which gets you to the same point. Now, both of these obstructions signal a slowdown, but not necessarily a saturation of complexity growth. You have to work a little bit harder to see a saturation. Let me explain a little bit about conjugate points. So these are local obstructions, so they're much simpler to study than geodesic loops. So what is a conjugate point? We start at the identity, and as I said, we have this linear geodesic, which is running in a straight line to the time evolution operator. And let's suppose we encounter a conjugate point, which I've drawn in red. Now, a conjugate point means that this geodesic segment can be deformed into this curved segment in such a way that the length and endpoints remain fixed. So the length of this curved segment is equal to the length of the straight segment between the identity and this red point. Now, why does this mean that there's a shorter geodesic from the identity to the time evolution operator? Well, what we can do is instead of following the linear geodesic, we can follow this curved trajectory and then follow the original trajectory. Now, at this red point, the curved trajectory meeting the original trajectory has a kink in the path. So this point is not smooth if we simply adjoin the deformed path to the original one. And by smoothing out that kink, we can reduce the length of the curved path followed by the straight one. So what this means is we've constructed a curve from the identity to the time evolution operator, which is shorter, just explicitly has a lower length than the length of the linear geodesic, because we're able to smooth out the kink in this deformed path. So this is why conjugate points signal an obstruction and in fact a slowdown of the distance growth and therefore of complexity growth. Now, one of the main outputs of our previous work was we defined a super operator, which I've written as bold Y, whose zero modes are in one-to-one correspondence with conjugate points along the linear geodesic. So if we find a zero mode of Y, we found a conjugate point. We found one of these red points. So here's the super operator Y. The precise form is a little bit complicated. It takes some input, delta V0. And the only thing I want you to take from this stage is that there are three terms in Y. The first term is this one here. I've drawn in brackets 3 terms. The first term is here, and this subscript L means a projection to the local subspace. So we had a space of generators, and we had a subspace which was considered local or simple. Those were roughly our quantum gates. And we had a subspace that was considered non-local. And this L means project delta V0 to the local subspace. Now, the second term involves the non-local indices. You can see the dotted indices here, but it also involves a projection to the local subspace. So you might think of the second term as the mixing term between the local and non-local subspaces. And this final term depends only on the non-local indices, these dotted indices. So this you might think of as the non-local term. So that's what I want you to take from this expression. The first term is the local term. The second term is the mixing term. And the final term is the non-local term. That's the important structure. Now, the starting point of this more recent paper is a much simpler way of thinking about the superoperator in certain cases. So we can assume that the input is an adjoint eigenoperator, where by that I just mean the input is a creation annihilation operator, which is either purely local or purely non-local. So on these restricted inputs, the superoperator simplifies greatly. And the reason it simplifies is that the mixing term vanishes. So when the mixing term vanishes on these inputs, the superoperator Y has the following form. So again, the subscript L means local projection. The subscript NL means non-local projection, projection to the hard subspace of operators. And it depends only on this function phi. And you can see that phi is this simple exponential -1 divided by ix. And so now we can think about what happens if we feed a local operator to y. So if we feed a purely local adjoint eigenoperator, we just obtain the first term, because the non-local projection will kill the second term. And the first term, we can see that the function y, the function phi, has a 0 at t equals 2 pi over lambda. So this function phi has a 0 at x equals 2 pi. So when lambda t equals 2 pi, t is equal to 2 pi over lambda, and there's a 0 mode of y. Now, similarly, we can feed a purely non-local object O into the superoperator, which is an adjoint eigenoperator. And we find that, again, we find the function phi, but the argument of phi is just weighted by the parameter 1 plus mu. So here mu is appearing explicitly in the formulas. And we can see that there will be a 0 mode, but the 0 mode will now be at time equals 2 pi over lambda multiplied by 1 plus mu. So the 0 mode has been shifted by a factor of 1 plus mu. And this almost immediately proves our first theorem on the growth rate, because there is a 0 mode, as I've described, and hence a conjugate point when x is equal to 2 pi. And so this first case is the local case, where the k locality of this O is less than or equal to that of the Hamiltonian. And the second case is when k is greater than q, when it's more non-local than the Hamiltonian. Questions about this? All right, very good. So the second theorem assumed that this matrix MAB that I defined for you before has a 0 mode. Now let's just give this 0 mode a name. Let's call it X. Then it turns out by analyzing explicitly the matrix Y, we can compute its Frobenius norm. And it turns out the Frobenius norm of Y is just equal to this expression as a function of X and M. So M appears explicitly, and X is being fed into M as a matrix. Now, by assumption, X was a 0 mode of M, so this expression is identically 0. What that means is the Frobenius norm of Y is also 0. And so therefore, Y applied to this input X must vanish. What this theorem is supposed to show is that a 0 mode of M corresponds to a 0 mode of Y. So it's not true that all 0 modes of Y are of this form, but if M has a 0 mode, then there exists a 0 mode in Y. So what that shows is that there is a conjugate point when you have a 0 mode of M, and therefore a complexity slowdown after that 0 mode. That proves the second theorem. And just as a remark, such conjugate points are quite special. Their locations are actually independent of the cost parameter mu. So if you encounter one of these conjugate points, a 0 mode of M, at a fairly early time, then you might be in trouble from a complexity growth rate standpoint. If you're hoping that your complexity grows for a very long time, you better not have any of these conjugate points, any 0 modes of M. Questions about the second theorem?
Yeah, actually, I would like to ask, your zero mode here means like the function of phi goes to 0?
Sorry. So the function phi is not involved in the definition of M. So let me just remind you, M looks like this. So the function phi only appeared in the first theorem, where we assumed that the input to the superoperator was a k-local creation annihilation operator that satisfied this condition. But here we're just coming up with some other characterization of a zero mode of Y. So we don't have to assume the input is some creation annihilation operator. We can instead look for a zero mode of this matrix M, and that will correspond to a zero mode of Y.
Yeah, but like, how do you define the zero mode of your matrix M?
So this matrix MAB, so this is the matrix element labeled by these two indices. These are two local indices. So there's some space of operators, and this is a square matrix acting on this particular subspace of operators, and we just look for a zero eigenvalue. So we calculate the eigenvalues of that matrix at any time t, and if there's a particular time at which we see that M has a zero eigenvalue, then we know that there's a conjugate point.
Okay, thanks.
It's just the eigenvalues of that. Yeah, very good. All right. So now we can apply these theorems to free, integrable, and chaotic systems and try to extract some results about the plateau height. So let's start by applying our creation annihilation theorem to the Q equals 2 Hamiltonian. So this is the free Hamiltonian. We have some couplings, Jij, and here are two Majorana fermions. Now we can change to a basis of n/2 Dirac fermions and diagonalize H, of course, because this is free theory, and we obtain the following object. So these J3s are diagonal matrices. They're diagonal in the energy eigenspace. They have inputs plus or minus 1, matrix elements plus or minus 1, and there are some omega p couplings that appear, which are roughly the eigenvalues of this matrix J. Now, in the Dirac basis, the total space of operators splits into n/2 SU2 algebras that are roughly as follows. So these A dagger and these AP daggers and APs are the Dirac fermions, and J3 is just the usual J3 of the Pauli algebra. So we have n/2 copies of this algebra, and we'll sometimes refer to AP dagger and AP as J plus and J minus. So P is an index that runs from 1 to n/2. So this is just a particular change of basis of our Majorana fermions. And in fact, in this basis, this nice Dirac basis, there's a complete basis of operators consisting of only eigenoperators for H. So the whole space of operators can be cast as eigenoperators of the Hamiltonian in this case. And so the way that goes is as follows. This is kind of complicated formula, but the general basis of operators can be written as a product of all possible J's from the first algebra to n/2. So you pick one J from each of these n/2 algebras, and this index beta can be either the identity, so 0, it could be J plus, it could be J minus, or J3. And the way that the eigenvalue is calculated is you look at these indices and you look for the J pluses, and if you see a J plus, you add that coupling, omega p, and if you see a J minus, you subtract the corresponding coupling. So that's how the eigenvalue is computed. So now we have a full basis of operators, which are all eigenoperators. So the creation annihilation operator, the creation annihilation theorem, tells us precisely where all the conjugate points are in this model. So in the free theory, we're able to use that theorem to extract the location of every conjugate point. Now, in the free theory, we consider operators that are at most too local to be simple in the complexity theory sense, because we have Q equals 2. So all conjugate locations are of the following form. So that the one local operators correspond to conjugate points, which look like pi over omega p. So a single coupling appears in the denominator. And we have copies at integer multiples of this expression, of course, because phi is a function that vanishes at integer multiples of 2 pi. The two local conjugate points correspond to times which look like this. where we have a sum of omega p on the denominator, because there will be two omegas that appear in the eigenvalue up here. And similarly, we can have a conjugate point associated with an object that looks like a dagger A, or AP dagger AQ. And so the AQ comes in with a minus sign in this eigenvalue. So these are the conjugate point locations that are independent of mu. So these are the local conjugate point locations. Now there are also non-local conjugate points, which correspond to eigenoperators that are more non-local than the Hamiltonian. And those conjugate points are of the following form. So this object is a 3-local conjugate point, and it comes weighted with a factor of 1 plus mu. And this final object is an n-local conjugate point. It involves, this particular one corresponds to all j plus. So a dagger 1, a dagger 2, and so on, all the way up to a dagger n over 2. So these are all the conjugate point locations. Now, using these conjugate points, the free theory is actually simple enough that we can even find the new global minimizing geodesics, which replace the linear geodesic. And the general strategy, I'll go through this a little bit quickly, but feel free to ask me questions at the end. The general strategy is to find a local model of the conjugate point by isolating a subalgebra of SU2 to the n over 2 that captures just the relevant degrees of freedom. And by a relevant subalgebra, what I mean is a projection of the Hamiltonian to the subalgebra along with the operators that correspond to the conjugate point. So the creation and annihilation operators that give you the conjugate point along with the Hamiltonian. And as an example of this, we can consider the one local conjugate points. So remember, these are associated with operators AP dagger and AP. And to find a relevant subalgebra, we just project H to this subspace. And it turns out that the projection, the minimal choice of projection is just to take the J3P term in the Hamiltonian. And that closes with AP and AP dagger under the Lie bracket. So it closes into actually a copy of SU2 that I wrote down before. And this exponentiates into a copy of the group SU2, which captures the relevant motion. So SU2 looks like a 3-sphere from a geometric standpoint. So here I've drawn this 3-sphere. The north pole corresponds to the identity operator, and this green curve you should think of as the linear geodesic, where we just point in the direction of time evolution and start moving. Now this T star is the conjugate point at this location, pi over omega p. And you can see that when we encounter this conjugate point, if we continued along the geodesic afterwards, the linear geodesic, there's a faster way to reach this point than the green curve. The faster way is just to go the other way around the 3-sphere. So these conjugate points, the one local conjugate points, correspond to south poles of 3 spheres. So just like on the surface of the Earth, if you start at the North Pole and go down to the South Pole, if you take one step beyond the South Pole, it was much faster to just start going the opposite direction from the North Pole. You would have gotten to your destination faster. So that's the way that the one local conjugate points yield geodesic loops on the manifold. It turns out that the two local conjugate points have a similar interpretation. It's a little bit more involved to see, but they can be interpreted also as south poles of 3 spheres. Now the upshot is that we can immediately write down the new geodesic that replaces the linear one, again, just by pulling the geodesic around the sphere as I described. So the general form of the velocity, so the velocity is no longer constant in t, but it depends on these parameters that I've labeled Cp, and the time derivative of these objects is always equal to omega p. But there are bounds on their values. So these individual coefficients Cp are bounded by minus pi to pi. So you can ask what happens when this linear function Cp grows and hits pi. Well, it needs to wrap around to minus pi. So we just make the replacement Cp goes to minus pi. Now that's from the one local conjugate points, and the two local conjugate points yield restrictions that look similar but are a little bit more involved. So these two local conjugate points yield restrictions on the sum and the difference of any pair of coefficients Cp. Now, given those restrictions, all coefficients of the velocity are now bounded, and so we can actually immediately place an upper bound on the plateau height Cmax by using the velocity of the maximum magnitude of Cp. So of course, all Cp's are less than pi, so their squares are less than pi squared. And here's the length formula. We simply plug in that velocity that I wrote on the previous page into this expression, and we find a sharp bound on Cmax, which is less than pi squared, summed over n over 2 terms. So for free theories, we have that Cmax is of order square root of n. Now, this isn't the sharpest bound, so I used only the one local conjugate points to write this down. So there's a sharper bound, but it's a little bit complicated to write down. Now, a bound of this order was actually known in the complexity theory literature before by these authors, Aharonov and Attia, but our conjugate point and geodesic loop analysis improves it by a constant factor. In fact, due to the incorporation of 2 local conjugate points, which actually lead to faster geodesic loops than the 1 local conjugate points. And to my knowledge, this is the first improvement to a known quantum algorithm that was revealed by the geodesic complexity formalism, which was part of the original motivation for its development more than 15 years ago. We were pretty happy about this. It was kind of a trivial improvement to the algorithm because we were only able to get a constant factor speed up, but we were pretty happy with this regardless. Okay, I think I'm going to skip the integrable section. Yeah, sorry, question?
Can I just have a question about what you just did? So do you have like an intuitive understanding of like what shortcuts are, like what kind of operators generate the shortcuts, like in physics terms? Like if you take, say, the Hamiltonian, that would be like the, I don't know, like the Dirac-Feynman Hamiltonian, for example, right? Like you evolve with the Hamiltonian, and then suddenly some shortcut appears, right? Like, so what's the nature of the shortcut?
Right. So the one local shortcuts, so the shortcuts which lead to this simplification arise directly from the individual Dirac fermions. So the A dagger and the A. So the individual Dirac fermions lead to this shortcut. To the stronger shortcut, the 2 local shortcut, you have to take a product of 2 Dirac fermions. So you have to write something like A dagger 1, A dagger 2. So that's the interpretation of something like this. And the interpretation of one of these final 2 local conjugate points is an operator like A dagger 1, A2. So it's a mixture of a Dirac creation and a Dirac annihilation operator. So that's the physical interpretation. Sorry, do you have another question?
No, that's fine.
Oh, okay.
Yeah, I mean, maybe I should let you finish actually.
Okay. Yeah, I'll just flash this this slide. So this is a numerical plot of the bound that I described above. So not the one that I wrote down, but the sharp one that incorporates the 2 local conjugate points as well. And you can see that at very large n, this complexity shows a very clear plateau that is very smooth. So these sharp points at small n correspond to encountering these south poles of 3 spheres where the velocity jumps. But you can see that at large n, you're encountering so many of these conjugate points that it smooths out the shape of the curve. Good. Let me skip the integrable section. I'll just say that you should see the paper for some details. The main message of the integrable section is that we consider Hamiltonians of this form. So we have some couplings, and we make our Hamiltonian out of J3. So this is the key simplification that we take in the integrable case. So this is not a 2 local Hamiltonian. It's actually 2k local, where k is some parameter that appears. And the bound that we obtain is actually just obtained in the same way as in the free theory. So we're able to write down some geodesic loops. Unfortunately, we don't have a full understanding of conjugate points in this case. So we cannot say that our bound is extremely sharp, but it is an upper bound. So we're able to find enough geodesic loops to at least generate an upper bound of order polynomial in n. The precise power, again, turns out to be q over 4. Good. And so here's a plot of an integrable bound. So this is the bound on the integrable Hamiltonian. Now let me talk about chaotic theories just very briefly. So for these types of theories, one of which you may be familiar with is the Sachdev-Kitaev model. We unfortunately have much less control over conjugate points and loops, but we can make some progress by applying our second theorem on the growth rates, this matrix M. And we can rewrite M in spectral form. So we decompose it into Hamiltonian eigenstates, and this function G appears. Where G is some ratio of sine x over x squared, and delta Mn is just a difference of eigenvalues. Now, so we have these TA and TB are some k local operators that we're taking the matrix elements of. in the Hamiltonian eigenbasis. Now, it's tempting to evaluate M using the eigenstate thermalization hypothesis for the simple operator matrix elements. Some of you might be familiar with this. ETH more or less says that these simple operator matrix elements should have a diagonal component as well as a component which is suppressed exponentially of the entropy of the system. And these parameters RMN are Gaussian random and have variance 1. So they're independent Gaussian random and have variance 1. There's a technical reason that we can't do this. It's because the sums in M run over the whole spectrum, and there are constraints on combinations of the matrix elements. So this was very fast. I can say more about this at the end if you have questions. But the upshot of this that I want you to take away is that it's not consistent to apply a sort of ETH ensemble over these RMNs to get an estimate of the matrix M that I wrote down on this previous slide. So we need a different way to get an estimate. Now, a better choice is to consider chaotic eigenstates to be a Haar random rotation of a simple fixed basis. So what we're going to do is write down these chaotic eigenstates as a Haar random rotation U of some fixed basis I that I've labeled with P. So U is drawn from the Haar ensemble. And this is actually true in random matrix theory, where the spectrum decouples from the eigenstates. And similar techniques have been recently used to gain intuition about the gravitational path integral by these authors. So here's the upshot of that calculation. I won't do it in any detail, but we can estimate the mean and variance in that ensemble of the matrix M by using Haar integrals over U. So what we find is that the average value in a typical chaotic Hamiltonian in that ensemble of MAB is something which is proportional to the diagonal matrix. So this matrix certainly has no zero modes. The average of this matrix certainly has no zero modes. And in fact, this parameter, this coefficient of the diagonal, is extremely large. It's exponentially large until a time which is order exponential in n. So until this t becomes of order 2 to the n over 2, this coefficient is very large. But once t reaches exponential time, this coefficient becomes small. Now we can also compute the variance, and we find that the variance of the elements is always of order 1 on both the diagonal and the off diagonal. And the only assumptions that we need to prove this are about the energy spectrum, and it should contain an exponential number of states, or order e to the n states, in an energy window that is polynomial size in n. And that's certainly true, for example, in the SYK model, as well as in black hole microstates. You can just explicitly check what the spectral width is, and it's polynomial in n. So what we see from this is that it's highly unlikely, using this theorem, that M has zero modes before exponential times. But once we reach exponential times, it's actually quite reasonable that M would have a zero mode. So at least we can show from this analysis that there are no conjugate points which are independent of mu before an exponential time. But when we reach an exponential time, we might encounter some conjugate points that are independent of mu. Okay, and let me just flash the analysis. So you have to do some complicated Haar integrals to analyze all this. This is the computation of the ansatz, an ansatz for the density that we use to extract this prefactor. To compute the variance, you have to do a much more involved calculation. There are actually an 8-term Haar integral that you have to do. There are some additional structures that appear that make the calculation more complicated. You can see the paper for more details. I'm happy to explain this as well afterwards if people have questions. So again, the upshot is that a typical MAB in a chaotic theory is a matrix with a very large diagonal and small off diagonals until a time which is exponential in n. And so it's unlikely that we have zero modes before that time scale. But once we reach that time, it is likely that we will encounter conjugate points. So this does not prove that the complexity reaches exponential heights in chaotic theories, because we have not understood the geodesic loops. So geodesic loops are extremely difficult to understand in chaotic theories. And personally, I have no idea how to understand them. I've tried to think a little bit about this, but it seems very, very difficult to do a calculation. What this does do is it gives us some evidence that very general properties of chaotic spectra and eigenstates lead to prolonged complexity growth until a time of disorder. So I hope that by explaining this geodesic loop caveat, I've told you what this approximate symbol means. So we're able to show that there probably aren't conjugate points until an exponential time. And at exponential time, there will be some conjugate points. But geodesic loops, we don't have any control over. Okay, so let me just finish up with some outlook. In my opinion, one of the very exciting takeaways of all of these results is that circuit complexity growth can be characterized using quantities that are much more familiar to physicists, like thermal two-point functions. And other notions of complexity have also recently been understood in this way. What this means is that it should be possible to do precision calculations of complexity directly in semi-classical gravity using the new wormhole and ensemble technology that some of you might be familiar with. Now, this is a natural next step beyond the calculation of entropies, as it's relevant for both the description of both global and local interior quantities, like the volume of maximal slices that I mentioned before, or maybe even the experience of the infalling observer. And I'm currently exploring this direction from several perspectives. So let me just flash a summary. What we did today, I hope I presented to you two theorems about complexity growth rates, and roughly speaking, the existence of creation annihilation operators leads to growth slowdowns, and the existence of zero modes in a matrix of smeared infinite temperature local operator two-point functions also leads to growth slowdowns. I also showed you a hierarchy of plateau heights in free, integrable, and chaotic theories that we understood with varying degrees of precision. So we were able to understand the free theory in a lot of detail. We had control over geodesic loops and conjugate points there. And we showed that the plateau height was square root of n. In integrable theories, we understood some geodesic loops, which gave us an order polynomial in n bound on the complexity height. And in chaotic theory, some very general properties led us to an approximate upper bound. We were able to show that the complexity reaches that upper bound modulo this concern about geodesic loops that we were not able to understand in the chaotic theory. And just as some highlights, our results in the free theory improved an existing bound in the complexity literature, and the chaotic theory our arguments only relied on properties of the spectrum and eigenstates. So let me finish there. Thanks.
Thanks for the great talk, Arjun. It's very interesting. I guess we can still take a few questions from the audience.
Mm-hmm.
Could you specify a bit more what do you mean by integrable theories?
Yeah, absolutely. Let me go back. So I only flashed that slide very quickly. So this family of Hamiltonians, for the purposes of this talk, this is what I mean by an integrable theory. So these J3 operators are some particular linear combinations of the Majorana fermions. Actually, they're quadratic combinations. So each one of these J3s is a two-local operator in the Majorana fermion language. But these, remember, they came from the Dirac fermion basis, where we had diagonalized with the free Hamiltonian. So these are related to the original Majorana fermions, but this Hamiltonian is not two local. It's actually 2k local, or k is the number of J3s that we include.
So is it, it's an interacting theory? Exactly,
that's right. That's exactly right. It's an interacting integrable Hamiltonian. Yeah. And the reason it's integrable is that this Hamiltonian has exactly the same eigenvectors as the free Hamiltonian, because remember that these J3s were diagonal in the free Hamiltonian. So they were just taking a product of diagonal matrices in that eigenbasis. So of course, the Hamiltonian will continue to be diagonal if we just have a product of diagonal matrices.
Could this be rephrased in terms of like a complete set of commuting operators with a Hamiltonian?
Yeah, it could. The only thing is that we don't actually know what those operators are. So there of course is a commuting set of operators with this Hamiltonian, but it's unlike the free theory. So in the free theory, let me just remind you, in the free theory, we knew what the complete set of, we had a characterization of the full space of operators in terms of eigenoperators of the Hamiltonian. So those were these products of J3s. And we actually knew what the eigenvalue was even. Unfortunately, in the integral case, the commutation of this Hamiltonian with one of our previous creation annihilation operators, it turns out that it's not quite the same. So this is a more complicated Hamiltonian, and the commutation relation is not as simple as the one that I wrote for the free theory. So while this thing has the same eigenvectors as the free theory, the adjoint eigenoperators of the commutator of the Hamiltonian with some operator is no longer the simple Dirac basis. So it's not the same basis, it's going to be some rotation of that basis. And in general, that's difficult to write down. So that for that reason, that was precisely the reason that we did not have control over all the conjugate points in this model.
I see. Thank you very much for the detailed answer. Thank you so much.
Yeah.
Anyone else has a question? I actually have a question. So for the variance in the matrix, in the third model of the chaotic system, yeah, right. So how is it really true that the time dependence cancels for the variance?
Is it true that the time dependence cancels for the variance? No, so there will be non-trivial time dependence. Yeah, good question. So there will be time dependence. The only thing that I wanted to say about the variance is, yeah, we did not extract that in the paper. The only thing that I wanted to say about the variance is that it's order 1 as a function of n. So there will be some time dependent factor that sits beside this term. We weren't so interested in what that was because we cared about the n dependence of this quantity. So as long as the n dependence was order 1 and not large compared to n, we were happy. It's enough to conclude what we wanted.
Yes, but the thing is that the time can goes to e to the n, and if time goes to e to the n, and the time dependence, for example, here will be, say, linear or some polynomials in time, then the variance becomes quite large.
Yeah, that's a great question. So what we wanted to conclude here was that at very large n, the diagonal is the dominant object until an exponential time in n. And that's true unless this variance is order e to the n. And so we were able to show that this variance is not order e to the n, it's only order 1 with n. If there's a t that sits beside this, it doesn't change that conclusion. You would need to go to an exponential time for this diagonal to become comparable. Yeah. But it's certainly true what you say, that at an exponential time in t, these variances become important. They become important in the calculation of the eigenvalues of this matrix. And because the we suspect, okay, I don't have a proof of this, but I suspect that what happens is that at exponential time, just as you said, there's a buildup of conjugate points. There's a buildup of conjugate points that happens because this variance is becoming comparable to the diagonal. And if I think about just a matrix with random entries, I can't guarantee that it doesn't have a zero mode, right? In fact, it's likely that it will have a zero mode for some values of these parameters. So there would be a buildup of conjugate points at a time which is of order exponential in n. And I suspect, I don't have a proof of this, but I suspect that that buildup of conjugate points is actually responsible for the plateau. That it's enough to understand that buildup of conjugate points, and you would actually be able to see the plateau coming out of that. But again, we don't have a lot of good control over what actually happens on the plateau. Yeah, okay. I agree completely with your intuition. Yeah, at exponential times, these variances become quite important in the calculation. But the point of this analysis that we did in this paper was just to show that that does not happen until exponential time.
Okay, sounds great. Okay, I guess nobody else has any question. So thank you very much again for the wonderful talk and the thorough explanations.
All right.